So rows will be this way, rows, and columns will be top down. There's a column. So what it means is that there are 640 columns over here. 640 columns. And then for the rows over here, there are 480 rows over there. Hence, making the giving the resolution for the image. So sometimes column is also called width. And sometimes row is also called height. So these different terminologies that is being used. So normally is defined by a column. We have the column by the number of rows. So this is one of the things that determine the quality of the image. So there are two things. One will be resolution, that is number of pixels. The other one will be quantization that I spoke about just now. So quantization is about how accurately the signal can be converted to digital form. Another way to think about it is this number of gray shades that's available. So number of gray shades that relates to the number of bits. So if the bit is just 1 or 0, that means 1 bit to the power of 1. That means the image will only get you black. So what I have over here is an image. You know this?
No.
Thank you. It was about 3 years ago when I was in. So what I'm going to do to this image is in color form. And you know, in Microsoft Paint, you can actually save it in 2-bit. If I were to save it in 2-bit, 2-bit is black or white. Black or white. So if I were to save that, let's call it save it differently. So save it in 2 bits, only black and white. Okay. What I want you to take note is that this black, you see that you will still maintain to be black. And then whatever color contrast in between the black to the white, whatever is in between, those that are not very black, 50%, those that are not very black, that means you will turn into white. Those are black enough, more than 50%, you will turn into black. Right? So this image here is going to turn into this. So you can see that the hair still maintained to be black, and then my face also turned black because it's dark enough, more than 50%. And then the background there's some colors just now. I can't go back because one is saved in monochrome, then it's that way. So the white part, the brighter background, it will be all changed to 1 signal, because it's only 1 bit signal. It's either 0 or 1. So that's for a 1-bit system where you have S0 or 1. Now obviously that's not going to be sufficient quantized level, so you need, let's say for an 8-bit system, you get 256 grayscale level. 256, that is from 0 to 2.5. Now, so there are 2 things that relates to the quality of the image. The first one would be your resolution, and then the second one will be your quantization. So quantization and resolution, they are independent of each other. If you want a good quality image, your resolution must be high and your quantization levels must be high. There's a larger number of bits. So you need these two to be adequately high. Now let's have a look at how can we improve or process the image. There's this technique that's called histogram analysis. So if I were to look at a figure or a picture, so a picture just like this. So out of this picture, I'm going to use this histogram technique. And the histogram technique says that I'm going to collect all the pixels that has a certain light intensity, right? So let's say a light intensity of 100. So out of this entire image, I'm going to take all those that is at an intensity 100, and then I count how many are there, and then I put it into this histogram. Right. So this histogram, at this scale, this axis over here is your gray scale. So the gray scale tells you how clear it is or how bright it is. And then this axis over here is telling us how many number of pixels that has that number of the gray scale. So let's say for, there's no 100, let's say for 150, it's about maybe 5,000 number of pixels that has 150 gray scale. So this is what we call a histogram. So this kind of sketch is a histogram. And we can make use of this histogram image to do some processing work so as to improve the quality of the image. We use a technique that's called histogram analysis. So histogram analysis can be used to determine a cutoff point to convert the image into a grayscale. We can use that to determine the level of noise. And we can also use this technique to separate an object from its background. Let's have a look. So for this image, it ranges from over here that is about 120 to this level over here that is about 180. So how many bits do you think this image is by looking at this scale? How many bits? 8 bits, right? To the power 8, that's 256. So this one is an error. It should be 255, 0. So for 256, so you can see from 0 up to somewhere here, that's 256. So that should give us an 8-bit grayscale. So the image turned out to be grouped between 120 to 180. So if you have something, an image that is doing that, what's going to happen is that the image quality is going to look like this. So the image quality looking like this is not clear to the human eye. So how then can we improve on the quality of this image? What we can do is to space out this spectrum over here. Space out. So right now, in between them is 4 grayscale levels. So if we space it out to 17 gray level scale, that means the same kind of image, but you kind of like space it out between 0 to 256. Now, if you were to do that, you could see that the quality of the image kind of improved. So this one over here is not that clear. This one over here, you can see much more clearer this line. So after you have processed this image, then we could extract information. Okay, so the first step is processing that image. So this is one of the techniques. By equalizing the grayscale across the entire grayscale spectrum. So equalizing means that there's a similar step size. Distribute that image out so as to improve on the lower grayscale and the higher grayscale so that you get a better contrast of the image. So over here, you can see that at 0, there's no extreme darkness in the histogram. So you can see that while all these places over here is kind of dark enough, but it's not really very, very dark. And the same goes for here. You can see that there's no extreme brightness in the histogram. Yes, these are the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. This one should be 16. 16 levels. And each of these interval is 17. There's 16 grayscale levels. So this is one technique. Another technique is called thresholding. Now, thresholding works in the following way. If I were to show you an example of an image, all right, all these words, then I'm going to use the following figure to so this is the grayscale level of that image. Thresholding just means that I'll set the threshold level. Let's say I set to 60. And I tell myself, going pixel by pixel, if any of these pixels were to be more than 60, which is my preset threshold, if it's more than 60, I'll push it up to the maximum, 255. Is 255 dark or bright? Bright. It's bright. So that part now, the object is going to look very bright. So later on we'll talk about why I set it to 60. If I set it to 60, any numbers, any grayscale numbers that is more than 60, I push it up to the max, 255. Anything that's lower than 60, I push it to 0. So it's either 0 or 255. So this kind of thresholding method, you can see now a very clear view of that object. I could almost see the object over here, right? And the others are all zeros. So this is enhancing the image, just like the 1 and 0 bit that I did just now, to bring out the contrast so that I could see the object very clearly. So, and how do we go about deciding this threshold level? There's a way to decide that. Maybe if I would do a sketch, this x is number of pixels, and this axis is your gray level. So let's say if I have an image that looks something like this. So just quickly sketch out and see. Noting that this x-axis is a grayscale level. So you have an image just across one slice where you have bright, dark, that way. So originally, maybe the threshold that we set, maybe about here, what we call 60, say for example. But what we're going to do is to set the threshold level at this level that is near to the value. So these portions over here, they are called the values. Now, if we set the threshold at a level that's near to the values, what's going to happen is that we will then enhance the image contrast. Because anything that's below the value will be taken as 0. Anything that's above this value will be taken as very bright. So what's going to happen is that that image that you can see over there, all these parts here will be very bright, and then will be very dark at the valley, and very bright, and very dark, and very bright in that way. So this would bring out the image without losing some of this content over here. So this one technique that can be used. We call it the valleys. Where is that? Values are chosen as the threshold value. So in this case, it's multi-modal distribution. So this is a very simplistic way of doing the thresholding. There are actually more sophisticated techniques out there, but in this module, we don't really cover too much of it. You need to write a computer program, a simple routine, in order to process the image. Some of these processing commands are already available out there. So these days, it's actually writing that code down to do the image processing. This is an example of the various thresholding levels. So if you have the original image, that is 8-bit. So it's an 8-bit image. If I set the threshold to 100, compare it to 150, which one do you think gives you better, the 100 or 150? Better image. Not sure from the print, you see well. These two images, 100 or 150. Some would like 100, some would like 150. So it really depends on what you're after. If you're after this kind of details over here, then 100 will be good. If you're after certain other details, right, you can see here it uses that. If you're after this kind of zigzag details, then you have to assign a different threshold. So while the threshold is applied to one single row of the image, you have to look at the overall image. What are the features that we want to extract? Hence, this is the part that's your image analysis. So the processing part, techniques, that one can be applied. The analysis part, that one must come as well. If you are interested in the object overall shape or certain small details, then you have to adjust your thresholding specific to that detail part in your image. Because the entire image, there will be different details at different parts of the image. So it depends on which one you want to focus. Now, there's another technique that we call the spatial domain operations. So spatial domain is different from that frequency filtering technique that we saw, the thresholding, which also depends on what is the outline, the frequency spectrum of the image. Spatial domain is to apply a mask to your image and apply the mask pixel by pixel. So what is a mask? A mask is in a very brief word, it's just like a filter. Apply a small filter that is just 3 by 3 pixel, but we don't call it 3 by 3 array, we call it 3 by 3 kernel. So the 3 by 3 kernel, or we just simply call it mask, we apply this to one such pixel. So let's give you an example. So this image here, I'm not going to write numbers in there, but just call it A, B, C, D, so that later on you know what happens when you apply the mask on top of that. So this is an example of a mask. Usually there'll be numbers in there. Later on in the following page you get to see that. What is happening is that we're going to be focusing on this part of the image where we want to change this pixel that's called F. So after doing this masking, then this value in F will be changed. So how does it change? We're going to use this formula over here, this formula. And this formula is written out in that way, but I'm going to write the long version. So just for a 3x3 kernel R, which is the result, it's the pixel A multiplied by M1 plus pixel B multiplied by M2 plus pixel C multiplied by M3 plus ABCD M4 E M5 F M6 G M7 H 8 and last one I 9 Well, there's no H in your image. Okay. So this much E F G I J K. I can see that A B C E F G I J K. This whole thing divided by the denominator is what we call a normalizing factor S. And in this case, it's just adding up the mask values. So the mask value would be M1 plus M2, M3, M4, 5, 6, 7, 8, 9. So what are we doing here? We're using this kind of equation so as to come up with a value to replace F pixels. So this R here, after this kind of calculation, is going to replace this pixel F over there. This method, multiplying the mask to the image, is called convolution. So this word sometimes called superposition. That is multiplying and then adding them up pixel by pixel is called convolution. So if we convolute the mask to this part of the image, so as to change the center of this mask of this part of the image, then we can move this red box to the next part of the image. So we move on pixel by pixel throughout, so that we can get an enhancement out of it. Let's have a look at what is this enhancement. This is an example. In this example, this convolution mask is actually low pass. Later on, I'll tell you how to see low pass and high pass. This one over here is low pass. Actually, you know low pass because there's not much there on the So what I'm going to do is apply this convolution mask to this part of the image so as to change this F pixel. So F pixel now is 90. So what I'm doing over here, we'll be taking R equal to 20, the 1 times 20, 1 times 20 in that way, 1 times 20, 1 times 20 over here, 1 times 90, 1 times 20, 1 times 20, 1 times 20, and the last one, 1 times 20. So altogether, how many 1 times 20s are there? So there are 8 of them. 1 times 20. And plus the other one is 90 1. Divide by the denominator, which is your normalizing factor. So that will be adding up all the ones over there. So there are 9 of them. So if you do that calculation, you will get kind of like 27.778, approximately 28. So after you obtain that R, you can see that that image, it changes that 90 into 28 over there. This is applying a low-pass filter, pixel by pixel, by moving that mask through the entire image, moving that mask from pixel to pixel. So we can do this kind of, it's a little bit like filtering, it's called convolution of the mask. Now, there's another way to do this, there's another filter that you can apply. So in this case, this kind of filter is called high-pass filter. Now the high-pass filter, actually I want you to see this one, the mask is kind of like a flat plane. Whereas for this high-pass filter, you can see it's fast changing because it has got a higher slope from one pixel to the other pixel. It's got a higher, because it's like -1, and then you go to 4, it's -1, 4. So it's sort of like a kind of like a cone shape. If you can imagine that. This one is kind of like a cone shape. This one is kind of like flat. So the flat one, low pass filter. The one with the cone shape is high pass filter. So when applying the high pass filter to this image again, let's have a look. R equals to, there are going to be 4 of -1s, multiplying to 20. So 4 of them, 20 multiplied by -1, plus is 4 multiplied by 9. So it's going to, we call it 4 convoluted. So we have 90 multiplied by 4. And divide by the summing up of all this. If you sum up all this, what will you get? If you sum up -1 plus -1 plus -1 plus -1 plus 4. You get 0. So in this case, that normalizing factor, which is the denominator, we put it as 1. If we put it as 0, then that will get us 0. So this is a condition. If you have the mask giving you 0, then you replace the denominator, which is a normalizing factor, to be equal to 1. So if you work this out, you get 280. So you can see that 90 will be replaced by 280. So 280 will be now brighter. Right? So for that kind of image, after applying a mask, if it's a high pass mask, you can see now the high pass will pass through, the brighter one will pass through. And if you use a low pass mask, then that value in the center will become dimmer. So it depends on what kind of the results that you want, then you apply the necessary mask. After applying this mask or frequency techniques, or what we call the frequency or spatial techniques. Now spatial because we are looking at the space of the image and move that mask from pixel to pixel. After you've done that, then in our analysis job is to figure out what is the edge of the object. And there's a certain technique that you can use in order to figure out the edge. So over here, we have an image. We're going to define on as the blue color pixel. So the blue color pixel is on. The white color pixel, that means all of this, we call it off. So So the on pixel, whenever our program runs through the entire image, so we'll start by coming in over here. So when at the first change of that pixel, if it's on, then we'll tell our program to move to the right, to the left. So if it's on, these are the rules that we can place. So if it's on, that means blue color, then we move to the left pixel. If it's off, then we move to the right pixel. So on, which is blue. After that, we move to the left. Off, then we move to the right. So let's have a look at this. This is a technique that we can use to sense the edge of the trigger after you have processed the image. So we're going to come in one of the any entrance point. So you can see that there's no change. So you keep on moving, no change, until the first change, it hits blue. So if it hits blue, that's on. And if you have on, which way do you turn? You turn left, so you go up, left. So when it turns left, it senses that it's white. So if it's white, then you will turn right. And it senses white again, then you will turn right. And it senses white again, you will turn right. And it senses blue, then you turn left. Sense blue, turn left. Sense blue again, turn left. Now it's white. Sense white, turn right. Sense white, turn right. Sense blue, turn left. Got it? So this technique will trace the edge, going around and then going around. This, and then finally coming back over here. And then you start to sense that, hey, I've done this pixel before. Right? Because all these pixels would have whatever row or column number. Once it senses that it's back to that pixel over here, then it will stop. The program will stop. And then you retrieve all those pixels that it has went through before, all those blue pixels that it has went through before. Hence creating the outline of your image. This is called edge detection. We detect the edge of the object. This is one technique. So you can see that you need to do the programming work so as to be able to sense that edge. So when all the pixels have been visited, which can be marked, the object edge is produced. And once you have object edge, that means you have complete your analysis of the object. So in order to get this blue and white image, you would need to do the processing work. So the processing techniques that you learned before just now, thresholding, looking at the frequency, applying the filter, or using a spatial domain by applying the mask. All these are the techniques that's used to process it. And now that you use this edge detection technique in order to bring out the shape of the edge. Okay, so today we'll end early. I'll see you again on Friday.